We're going to do a quick recap of some of the analyses that we've been doing so far, including kind of comparing ANOVA and t-test to correlation and regression, reminding you a little bit about correlation analyses, and then getting into what a regression analysis is, why we might use them, how they're calculated. Now, one of the things that you will notice multiple times in here is I'm not going to I'll give you equations in a few places. I'm not going to have you calculate much of anything with regression. This regression can be a little bit more complicated, especially once we get into multiple regression. It can be a bit more complicated to calculate. And frankly, you're going to be doing most of this on computers. I'm going to teach you the kind of nuts and bolts of what goes into these calculations and what they mean. But we're going to focus more on kind of interpreting them and how we use the statistics that we would get from a statistical program. Most of what we've talked about so far with inferential statistics has been comparing group means. We've done this using t-tests and ANOVA. But what about when we have a continuous variable instead of a categorical variable? So we've talked about categorical variables like different groups, different treatment groups, freshmen versus sophomores versus seniors, things like that. But what about when we have a continuous variable? What about when we don't have groups, but we have one continuous variable predicting something else? This is where we get into correlation and regression. So let's say you want to know how SAT scores or ACT scores are related to college grades. Pretty useful to know, right? We have an assumption that students who get higher scores on the SAT and the ACT will also get better grades in college. This is a positive correlation because as one variable increases, the other one increases as well. Now we can also have negative correlations. Let's say the amount of time you spend playing video games and your college GPA. Presumably, students who spend a lot of time playing video games will spend less time studying, so they'll do worse in their classes. This will probably be a weaker correlation because there are going to be plenty of students who don't play video games at all who still bomb their classes, and there are going to be some students who play lots of video games but also do really well in their classes. But there will likely be some level of negative correlation, whereas time spent playing video games increases, the GPA decreases. So we've talked about correlation a bit before back in chapter 6. This is simply plotting the association between two variables by putting them on an XY coordinate on a scatter plot. But what if we want to make predictions? What if we want to predict your college GPA based on your SAT or ACT scores? To do that, we need to use regression. And we also have to use regression if we want to use more than one variable to predict our outcome variable. For that, I want to have you think back to the lesson on the Pearson product moment correlation or correlation analyses. If you haven't looked into it in a while, look back at that lecture video on how to calculate the R for two variables. Remember that we converted those raw scores into z-scores in order to put them on the same scale and be able to see which ones are high and which ones are low very easily by putting them in z-scores. And then we multiplied those together. We added up those products, and then we divided by our degrees of freedom. That's what you can see there in that equation. We could then square that number to get R squared, or the percentage of overall variability in the two scores that is explained by one another. Now let's take this SAT GPA example. We have variability in SAT scores. Some people score high, some people score low, but most people are kind of in the middle because it's pretty much normally distributed. Same thing goes for college GPA. Some people are high, some people are low, most are in the middle. What percentage of the variability in who scores high or low on the SAT is the same pattern as who scores high or low on GPA? That's known as covariance. It is how much they covary or how much they vary, how much they move around together, kind of holding hands. Now, the scatter plot that we have here shows the relationship between people's scores on the measure of anxiety and on a measure of depression. So depression is on the x-axis and anxiety is on the y-axis. The Pearson product moment correlation for this, our R value, is 0.543. which is a pretty strong correlation. Remember, a perfect correlation would look like a straight line of all of these points because variable A and variable B would move in lockstep. We have a really strong correlation here, so we can see that even though it's not perfect, there's a pretty clear pattern. But that's where correlations end. We can use critical values to determine if there is a significant amount of covariance compared to the overall variability in scores, but it doesn't allow us to actually predict anything. And that's where we move to regression. Regression analyses are at their heart an attempt to predict scores. We find a line that fits the data in the scatter plot, and then we can use that line to predict additional scores. And correlation, all it does is tell you about two variables, tell you about the data. This is like computing our standard deviation using a denominator of n, versus regression allows us to predict, to estimate. This is like our standard deviation, our S hat, where we are predicting the population standard deviation based on our samples data. So regression is an attempt, instead of just describing our data, which is what correlation does, a regression attempts to speak to the larger population, that based on our data, we can predict what the scores in the population would be. Now, so we have this line that allows us to predict or estimate what scores, if you know a depression score, predict what an anxiety score would be. This is referred to as the line of best fit, the regression line, or the least squares line. Now we'll talk about why least squares in a few minutes. But in the correlation chapter, this is something kind of weird that the book does. I don't like that they put they kind of mix up correlation and regression a little bit, because they did talk about the regression line in the correlation chapter. So they talked a little bit about it. Now, as with all of our basic mathematical lines, we use the basic equation of y equals mx plus b. However, in statistics, again, we're going to write it a little bit differently. We say y hat or y prime equals a plus bx. Remember that a is our y-intercept, so it is going to be where this line crosses the intercept or crosses the y-axis right there. And x right here, this bx, x is our value on the x-axis. And then b is the slope of the line. So that is how steep or how shallow that line is. And then we use y hat or y prime to indicate that we are estimating or predicting the y values rather than using them from actual data. The equation for our regression line in this scatter plot is y hat equals 6 plus 0.51x. So if I have a depression score of 17, I can plug that in for this x right here. And I can plug that in. Let me see, I think I've got a stylus of some sort in here. Maybe not. Okay, I'll just go with having, oh, is that one? Yeah, that's one. Okay, so I can take my value of 17 and put it in. Oh, that's not going to work. So I can put it in for that x. So I add that together. So I'm going to multiply my 17 times b, which is right here, that 0.51, and then add 6. So my predicted score, if my depression score was 17, my anxiety score should be 14.67 when I put that in. So I've got, let's say 17 would be about here. And then we go up and we're getting 14.67. So that's pretty close to 15. And that's where my regression line is. So that is how I can predict scores. Now, it looks like I don't have anyone who scored 17 and 14.67 because all of the data in this sample is integers. It's all whole numbers. But it can predict what the scores would be. And so we see that we have a score that is pretty close to that. So let's say we have a score of 17, and we'll say they're scoring a 14. So 14 instead of 14.67, that's pretty close. And the anxiety score is just below 15, so we're getting a good estimate. And so we can go through and we can say, if we have somebody in the population who has a particular depression score, then we can estimate, and that's why we're using this Y hat, we can estimate what their anxiety score would be based on their depression score. And that's what this regression line allows us to do. It allows us to make predictions about the population via that line. So why do we call it a line of least squares, though? It's because this line, the line that fits the data best, has the smallest squared deviation between what the line predicts and the actual values. Basically, it does the best possible job of predicting the data that we currently have. So we could have a line that goes like this. We could have a line that goes like this. But those additional lines do not do as good of a job of predicting the data that we currently have. And so a line of best fit, or a line of least squares, is going to do the best job of that. Now, here we have a scatter plot with a few data points from a study aiming to predict a person's mood based on the number of hours they slept the night before. We have our data points, and then we have 4 possible lines that we can use to compare to the data that we have. For each rule or line, they call them rules, but you can think of them as being lines, we have an equation. Using those equations, we can predict the mood scores we should get based on different amounts of sleep. Now, you can see the actual data here in these 2 columns. We have our number of hours slept, and then we have the actual mood score. And then we have rule number 1 is this line here. Rule number 2 goes straight across. Rule number 3 is here. Rule number 4 is here. And so rule number 1, this is the formula for this line. Rule number 2, this is the formula for this line. Here's the formula for rule number 3. Here's the formula for rule number 4. And we can go in and we can say, okay, here is our X. We have an X of 5 hours of sleep. And what do we estimate that we would score for each of those? So for this number of hours of slept, for rule number 1, if you had 5 hours of sleep, we would expect that your mood, using rule number 1 here, your mood would be 7.1. So if you slept 5 hours, we expect that your score would be a 7.1. Now, our actual mood was a 2, was much worse than 7.1. But that's what that line would predict. For rule number 2, right here, you can see that all of them are 4. And that's because our B is 0, meaning the slope is 0, meaning it's a straight line. So this says that rule 2 says that no matter how many hours of sleep you get, your mood is going to be a 4. This would be a null. This is basically a null hypothesis, saying that there is no actual association between your mood and the number of hours you sleep, because your mood is the same regardless of how many hours you sleep. Rule number 3 here, we have kind of this formula here. We can plug that in. So you get 5 hours of sleep. You should have a mood of 2.5. We get a mood of 2. That's pretty close. 6, you should have a mood of 3.5. We got a mood of 2. That's a bit farther off. 3.5 and 3, a little closer. 7 hours of sleep, you should be at 4.5. You're at a 4. So it seems to be overestimating a bit. And then we have this rule number 4. And rule number 4 just kind of eyeballing it, you can see that it's right on a few of the points. It's pretty close to the other ones. So it looks like it's going to be the best one. And then we can plug in our estimated values, what those values would be suggested by or what those values should be based on the line. And we've got 5 hours of sleep. We estimate you should be at a mood of a 2. Ooh, we are at a mood of a 2. Awesome. 6 hours of sleep, you should be at a 3. This person's at a 2, but 6 hours of sleep, that person is at a 3, and it's a 3. And so it's a pretty good estimate. So we seem to be pretty good here. So we can take each of these rules individually and actually compare them and see how much deviation, again, that squared deviation, how much deviation is there between the estimated and the actual value. I'm not going to go through all of the steps for each of them individually, but you can see here the calculations for Rule 1 and Rule 4. And then the sum of squared errors, or the deviation score, for each of the rules at the bottom. So we've got Rule 1. Here is our predicted value. Again, this is the same thing that we just saw here. We had it for Rule 1 and for Rule 4. We're not doing these two right now. So we've got it for Rule 1, we've got it for Rule 4, and we've got our deviation. So Rule 1 error. So how much error is there? What is the difference between what we estimate and what the line says we should, or what the actual value is and what the line says it should be, or what the equation says it should be? We've got quite a bit. We got some of them that are pretty close. Some are close there, but we've got quite a bit of deviation for these other ones. So that is our error. That is the amount of the variability in scores that is not accurately predicted by our equation. So we get our deviation score, our actual value minus the expected value, and then we square those. Same thing as when we were getting standard deviation and variance. We are squaring these to put them on the same, so that they're positive and negative. And then we're also squaring it to kind of emphasize those big deviations. Then we add them all up and we get our sum of squares. This is the sum of the squared error of the deviation. Now for this line, that sum of the squared error or deviation is 73.33. That's a pretty big amount of deviation, and that makes sense because there is a whole lot of deviation from what this line predicts and what the actual values are. Now when we look at line 4, or Rule 4, we're seeing a much smaller overall deviation. So with that first value, we put an actual value of 5, we expect a value of 2, and we get an actual value of 2. So there's no deviation. On the second value, we put in an x value of 6. We expect a 3, we get a 2, so we have a deviation of -1. On the next one, we put in a 6, we expect a 3, we get a 3. The next one, we put in a 7, we expect a 4, we get a 4. Again, no deviation. For 8 hours of sleep, we expect a mood of 5, we get a 7. We're getting a little bit of deviation there. We got a +2 there. And then for 10 hours of sleep, we are expecting you to have a mood of 7, and you had a mood of 6. Maybe you slept a little bit too much and you're a little cranky after that. So we got a little bit of mood there, deviation there. And then we square those, we square that error, and we get our sums of squares. Now, we didn't do this whole process. You can see the 73.33 right here, and the 6 is right here. We didn't do this whole calculation for Rule 2 and Rule 3, but you can see here are, I just kind of covered that up. You can see the squared deviations there, the sum of squared errors there for those other two. Now, if you look, our best fitting line is Rule 4 because it has the least error. It is the least squares. It has the smallest amount of deviation. And that is why it's called the line of least squares. So how do we actually calculate these regression lines? There are literally an infinite number of possible lines that we could test, because we could test different intercepts, kind of going back to these different rules. We could test different intercepts, different A values. We could test different slopes. There's literally an infinite number of lines that we could use. And do we test every single line? No, that is a waste of time. There are some pretty straightforward calculations on how you can get this. I'm not going to make you do those for this class, because honestly, it's unnecessary for this level of course. A lot of courses at this level don't even cover regression, much less multiple regression. But regression is incredibly common in real world practice. I use regression all the time. Regression is probably the most common type of analysis that I do in my research. We do regression all the time in healthcare, in business. You need to know what a regression is, and how to interpret it. You do not need to know how to calculate it by hand, because frankly, beyond this class, you're probably, or if you take an advanced statistics course, you're probably never going to have to calculate any of it by hand. So I'm not going to make you do that. If you want to learn how to calculate it by hand, how to find the slope of that line, it's actually not that difficult. I just don't want you to waste brain power on it for this class. The chapter will walk you through how to do that, but you do not need to know it for this class. You are welcome to skip over those sections. But if you are really interested, you want to understand more in depth behind it, the chapter supplement that I uploaded does walk you through it in a very straightforward manner. Now, one of the kind of fun and honestly sometimes kind of annoying things about statistics is that a lot of analyses are just other analyses in sunglasses and a fake nose. And correlation regression are one of those. When you have one predictor and one outcome, correlation and regression are the same thing. Let me say that again. Correlation with one predictor and one outcome, and regression with one predictor and one outcome, are the exact same thing. They are going to give you the same value for R and R squared, because all it's telling you is how much of one variable is explained by the other variable. They are the same thing. R and R squared for regression and correlation are similarly calculated the same way. So you have calculated R for correlation. Usually for correlation, we are using a lowercase r. For regression, we're using a capital R. But honestly, there is absolutely no difference between them when you have one predictor and one outcome. We're going to get into multiple regression in a few minutes, and that's when it's going to get a little bit different, just because you have multiple predictors. But when it is one and one, correlation and regression are the exact same thing. So you have your R and your R squared. Remember, your R is telling you how much does one variable predict the other one. Now, this is simply the table from the Pearson product moment correlation calculation video. I literally copied and pasted it from the correlation video. So if you want to walk through it again, I recommend doing it by all means. But basically, you are just making your z-scores for variable x, your z-score for variable y, in order to see, do the high scores in one, how do the z-scores, how do the high scores on one relate to high scores on the other, or low scores on the other. And then you multiply those together to see how that comes out, and then you add those together, and that is your R. And then you square that to get your R squared. So R times R equals R squared. And remember, R squared is your percentage of the variability that is explained by the other variable. So if we're going back to this, we have our R for each of these, and then you multiply them together for your R squared, and that tells me how much of the overall variability in these two variables is explained by the other variable. Equation for the line. So you've got your y hat equals a plus bx. So a is your y-intercept, and then b is the slope of your line. So, but we can use b. B is not just a number that exists. We can actually use it, as you've seen. B, the most important thing for you to remember is that B is the slope for the relationship between your predictor and outcome. This is sometimes referred to as the unstandardized coefficient. And we'll get to that in a minute as why it's called that. But basically, for every 1 point increase in X, your outcome variable, your anxiety, your Y variable. So for every 1 point increase in depression, anxiety will increase by B points. So if, let's say, take a really easy example. Our y-intercept is 0. Just make this really easy. We'll say that B equals 4. If the score for your X variable is 1, so we score a 1 on our x-axis, we plug that in. B is 4, X is times 1, so and A is 0. So our Y variable should be 4. We increase X by 1, make X 2, so a score of 2 on your x-axis. Our Y variable increases by 4. It increases by B. We increase X by 1 more. We increase Y by 4 more. So this tells you for every X number of points in variable X, so every 1 point in variable X, you increase variable Y by B points. So here, now let's put it back into our depression and anxiety data. So we start off with a depression score of 1. We plug that into our equation. So this is our equation for the line. We should get an anxiety score of 6.51. So we get 1 and we get a line is at 6.51. Now, remember, there's not a data point just at the line because all of these are integers. They're going to be whole numbers. But we got one data point at 6. It looks like we've got one data point at 7 here. A depression score of 2 is going to increase. We increase depression by 1. We're going to increase anxiety by about half a point. So our anxiety score should be, we go up to 2 here. And our anxiety score should be at 7.02. We got a score just above that. It's probably an 8. Now this predicted anxiety score jumped by 0.51. Same thing. Add 1 to our X variable, we add 0.51 to our Y variable, and so on and so forth. We do X is 10, Y is 10 times B plus 6, so 11.1. And using this, we can say, okay, we don't have an X value. We don't have anyone who had a depression score of 35. But using this regression line, we can predict what their score would be. Their score would probably be about 24. And this allows us to predict scores. Now, the B is called the unstandardized coefficient. And it is unstandardized because it is in the scale of the variables themselves. Now, this might not make a whole lot of sense right now when I'm saying like unstandardized versus standardized, but I'll talk about that more in just a minute, and give you another example where the variables are on very different scales. And so you can see that effect more. Now, in addition to calculating that unstandardized regression coefficient of B, We can also convert this into a standardized value known as beta. Just like calculating the regression line, the book walks you through this formula, but again, it's not particularly important for you to know. The most important thing is for you to understand the concept behind it. And that's that beta is basically the z-score version of B, meaning it puts it in terms of standard deviations. So for B, we said that every 1 point increase in variable x is associated with a B points increase in y, a B amount increase in y. Now, instead of talking points, like depression is on, you've got a range from 0 to 50. And for every 1 point higher your score gets, then your anxiety score gets, on a scale of 1 to 40, 0.5 points increased. Instead of talking points, we can talk in terms of standard deviations. So increasing x by 1 standard deviation is associated with a beta standard deviation increase in y. So here's an example. So B is 0.51, meaning that every point you go up in variable x leads to a 0.51 increase in variable y. In beta terms, every increase in variable x of 1 standard deviation results in a 0.32 standard deviation, so about 1/3 of a standard deviation increase in variable y. But why bother with beta at all? B, frankly, makes more sense because it's in real-world terms. The reason we need those standardized coefficients is that our behavior is never predicted by only one variable. We often want to put multiple predictors into the equation in order to improve our chances of accurately predicting our outcome. This is called multiple regression. So when we have multiple predictors predicting one outcome. The basic concept for multiple regression is the same as we've already talked about. We're just adding more components to the line. So instead of just having y hat equals a plus bx, now we've got the value of variable x1 and the slope for variable x1. So we've got a value and a slope for variable 1. We've also got a value and a slope for predictor number 2. We've got a value and a slope for predictor number 3. This allows us to do things like say that anxiety is a combination of depression levels and can be predicted by your current depression and your parent-child conflict and your friendship quality. Or your mood is predicted by the amount of sleep you got, the quality of sleep you got, and your current stress levels. Because mood is not only predicted by the amount of sleep you got. You can sleep a whole lot and sleep terribly. You can sleep a whole lot and sleep pretty well, but if you're really stressed, you're still going to probably be in kind of a bad mood. So we're not just predicted by one variable, and multiple regression allows us to see multiple factors going into these outcomes and measure the difference in the importance or the weight of each of those different variables on our outcome variable. So when we did a correlation or a single predictor regression, we could just use the same formula for calculating R and R squared using the products of those z-scores for each pair of values. We have more values in the formula now, but it's still the same basic concept. We are still looking at the percentage of variability that is explained by the model. So before, we were kind of using these values. We were looking, whoops, here we go, all the way over here. Nope, a little bit further. There we go. So we were able to kind of add these together, these z-scores, the product of those z-scores together in order to see how to create kind of this line and to see how much those values moved together. So how much of the variability in anxiety was predicted by the variability in depression. Now we're doing the same type of thing here, except instead of only having two variables, so we had a Venn diagram before with two variables, now we've got two predictors or independent variables, each contributing to a certain amount of variability in the dependent variable. So our R squared in a regression, we really don't use the R in regression. So remember, we can calculate R using those z-scores, but we square it to get the percentage of variability. We do the same thing in correlation. But in regression, we really don't use the R value alone at all. We only use the R squared. And this is because our R squared is very straightforward. You interpret it the same way. It is the percentage of variability in our dependent variable that is explained by all of our predictors. So it's adding this part here plus this part here and saying how much of the variability in our dependent variable is taken up by these independent variables. And our R squared, so our R squared, let's say our R squared is 0.432. This means that 43% of the variability in depression is explained by these independent variables. So 43%. There's still 57% of the individual differences that we can't explain yet, but we can explain 43% of it. That's really good. That's a big effect size because we're still using those same effect size measurements as we had done with correlation. Here I have the results from a study where I had anxiety being predicted by relationship jealousy. So anxiety here is being predicted by jealousy in relationships and depression and the participant's age. Ignore this line that says intercept. We really don't care about it. It is something that all statistics programs spit out. I have never used it in my life. So we're going to ignore it. But we have these three predictors in here. Now, our B coefficient, that unstandardized regression coefficient in Jamovi, is listed under this estimate column. And the beta is listed under the standardized estimate column. You'll see that in addition to the B and the beta, we also get a t-score and a p-value. This tells us whether that estimate is statistically significant. So this t-value tells us if 0.436 is significant. It tells us if 0.3925 is significant, if 0.0644 is significant. You can see here, based on the p-values, we can see that jealousy and depression are both significant predictors. So our null hypothesis here is that there is no association between jealousy and anxiety. There is no association between depression and anxiety. There's no association between age and anxiety. Now, our probability of getting the age scores if there is no association is very high. So this is not a predictor. Age does not predict anxiety scores. Now, most of the reason for this is, as you can see, or not over here, but most of the reason that age is not a predictor is because this was all done in college students, so basically everyone's the same age. That's a whole thing that we haven't gotten into about truncated range, but basically no, when everyone's the same age, it's hard to use age as a predictor. So we have these different values. So we can look at jealousy and depression here. Using the standardized estimate, we can see that the beta for age is extremely small. It would be for every one standard deviation increase in age, Anxiety decreased because it's negative here. Anxiety decreased. You'll also notice that it's negative here and it's negative here because it is a negative association. So for every 1 point increase in age, every one standard deviation, since we're looking at the standard estimate, for every standard deviation increase in age, anxiety decreased 0.0142 standard deviations. This is not a significant amount. This is a very tiny amount. It is not significant and we know this because the p-value is not significant. But now let's look at jealousy and depression. You can see that for every 1 standard deviation increase in depression, anxiety increased by 0.42 standard deviations. And for every 1 standard deviation increase in jealousy, anxiety increased by 0.303. But when you jump over to the B, those unstandardized B coefficients, we're seeing really big differences there. So the standardized estimates are pretty close, 0.3 and 0.42. But when we go over to these unstandardized estimates, you see that the values are extremely different. Depression is, for every 1 increase in depression, it is 1 point increase in depression, it is a 0.39 increase in anxiety. For every 1 point increase in jealousy, it is a 4.36 points increase in anxiety. Now that makes it sound like jealousy is really important for anxiety. That if you have any increase in jealousy at all, you're going to see a sharp increase in anxiety. But that's misleading. And the reason that this makes sense, because when we look at the standardized, jealousy actually has less of an effect on anxiety. A smaller increase in anxiety with every increase in jealousy, standard deviation-wise, compared to depression. So why the 4.36? Well, when you look over here at the descriptives, this is showing you the means and standard deviations, the minimum and maximum scores for anxiety, jealousy, and depression. Anxiety and depression are on roughly the same scale. The mean for anxiety is 11.9, depression is 11.6, standard deviation for anxiety is 8, for depression is 8.58. The minimum for all of them is 0, but the maximum score for anxiety that we see in our sample is 43. For depression, it's 38. For jealousy, it's 3. So the maximum score for jealousy ranged from 0 to 3. Anxiety ranged from 0 to 43, and depression was 0 to 38. So a 1 point increase in jealousy is a big increase. A 1 point jump in anxiety or depression is not that much of an increase. So this makes a lot more sense now when we see that 1 point increase in jealousy is associated with a 4 point increase in anxiety versus 1 point in depression, only 0.39 in anxiety. That's because depression and anxiety are much closer to the same scale. Jealousy is on a very different scale. So this is why these unstandardized estimates, even though they make way more sense when you're thinking about the actual regression lines and how the actual variables in real world data are associated with one another, how they predict increases in one another. The standardized estimate is much more useful in evaluating the impact of different variables compared to one another. So by using the standardized estimate, we can see that depression is associated with a greater increase in anxiety than jealousy is, meaning that depression has a greater association, a greater tie to anxiety levels than jealousy does. And that's when those standardized regression coefficients are really important. So we can look at we have this beta for variable X and the beta for variable Z. So this would be our variable X, this would be our variable Z. We're looking at the increase in Y. And so that allows us to really be able to compare these variables, because sometimes we want to say, well, which one's more important, jealousy or depression? If I need to focus on one thing, I want to do an intervention. Let's say I want to look at wound healing. And I can look at, we've looked at a number of different things before. We've said the location of the wound. Remember when we were looking at paired samples, t-test, we were looking at the location of the wound, or the healing the healing treatment, the intervention that we're using, or maybe some certain genetics, or the person's age. We can put all of those in here and use these standardized estimates to say which of these variables are most important to the healing process. Now, we might see that every single one of them is significant. Every single one of them plays a role in the healing process. But if we want to focus on one thing to improve people's outcomes after surgery, that's where we look at the standardized estimate, because it allows us, even because age and location and things like that, those are not going to be on the same scale. But we can use those standardized estimates to see how much of an impact does each of these have individually on the outcome. Now, I do want to mention, I've been using this example of the location. Location is a categorical variable. There are ways that we can statistically turn it into a continuous variable. We can do what's called dichotomizing the variable. If you ever need to do something like that, you have a categorical variable that you want to use in a multiple regression, there are ways to do it. Let me know if you want to do that. I'm happy to walk you through it. I have to do it all the time with my analyses. So like I said, I use multiple regression a lot, and I sometimes include things that would be categorical variables like race or gender. And I need a way to do that in the multiple regression format, which can only take continuous variables. It cannot take nominal variables. It's got to be ordinal, interval, or ratio. Really, it's supposed to be interval or ratio, but we can get away somewhat with ordinal. So I was using that example, but please don't ever put a categorical variable, a nominal variable, into a regression equation. It will completely screw everything up. But this is why B and beta are very important. And this is where, so in your homework, you're going to need to talk about the beta or the B estimate and what that means for increases in anxiety. You're also going to need to use the standardized estimate in order to compare one variable versus another one in terms of the importance of different predictors. The very last bit on regression is kind of a weird one, and that is that we also do an F-test, just like ANOVA. In fact, a lot of statistics programs will call it an ANOVA F-test. Because the F-test in ANOVA, we talked about it specific to ANOVA, but really what it's doing, is it's telling us how much of the variability in our outcome variable, how much of those individual differences in variable Y, in anxiety, or in wound healing are explained by our variables or our predictors, our model, and how much is not explained. So when we were doing an ANOVA, how much of the variability was explained by the group? How much of the variability in wound recovery was explained by the treatment group that they were in? And how much of the variability was still unexplained? Did we still have that there were these individual differences? That model fit is basically, if we're looking back, sorry, it's being a little bit weird, jumping all the way back to our scatter plot and our line. This right here, kind of to here, this is all variability in scores that we have not explained. That is all what is referred to as error. Remember again, error does not mean mistakes. It just means stuff we haven't explained yet. All of the stuff on the line, that is the variability we have explained. Now, the crash course video on regression does a really good job of explaining this F-test. It's also referred to as an omnibus test. Usually, it will always give you an F statistic, just like the ANOVA did. And it has the same basic concept. It is how much of the variability, what is the total overall variability? So we have the total variability over the explained variability. And then we are looking at the ratio of those. So our explained variability from the model, and that model can include multiple variables if you're in that multiple regression, or it can be one variable if you're doing just a simple one predictor regression. What is the overall variability, individual differences in this Y variable, and how much of it have we explained with our model? The more predictors we add in, the more we should be explaining. So we had our variability in depression that was being, or in anxiety that was being explained by depression, but then we added in jealousy and we added more predictive ability. We were able to explain more of the variability in people's anxiety scores when we added that extra thing in. So think about if we're talking about wound healing. How much of, or let's say we're talking about how well a student does in a class. I could say that I predict that how well a student does in a class depends on how closely they sit to the professor. I think this is important because if they sit closely, they're going to be paying more attention. They're less likely to get distracted because they know I can see them well. But if they're seated really far away, they might goof off a little bit more, things like that. But there are also going to be a lot of other things that go into whether a student does well or not in a class. Extracurriculars, their pre-existing familiarity with the subject, if they have a part-time job, if they get sick during the semester. So the more things I add into the model, doing this multiple regression, adding this variable 1, variable 2, variable 3, adding more and more predictors should get me closer and closer to explaining why somebody does well in the class or not. The problem is that the more predictors we add in, the more degrees of freedom we're using up. So then, remember that F test, if you have very few degrees of freedom, you got to have a big F there. And so we want to make sure that we have sufficient power, we've got a big enough sample size and things like that. So we can't just throw everything into an analysis. Just because that's just not good statistics. That's just not good science. We need to have pre-existing hypotheses and things like that. We can't just kind of what's called p-hacking, just go throw everything in and see what comes up as significant. That's just bad statistics and bad science. But the F-test allows us to say, we've got all of these predictors in here. How much of the variability is being explained? How much of the variability is not being explained? And how much power are we giving up by having too many predictors in that model? And that's where this F-test comes in. If you have a whole bunch of predictors that are not actually going to predict anything, so if you are looking at why a student does well in a class in college and you are asking about their grade in kindergarten, that's probably not going to have a huge impact, especially when you compare it to some other variable like their high school GPA. Their kindergarten grade in socializing probably not going to be super effective as a predictor. And And so that's going to take away, but we're estimating it. So that's going to take away some degrees of freedom. So we use our F-test the same way as we did in ANOVA. And it's basically saying, how much have we explained out of the total variability? And is the amount that we have explained significant compared to the amount that we haven't explained? So in your homework, you will present the F test. You talk about the F statistic. And the important thing to know there is if you have a significant F test, that tells us, just like the F test in ANOVA, that tells us that we're doing a good job of explaining the variability in our outcome variable. All right, so this is it for regression. Now, like I said, if you want to learn more about how those B coefficients and betas and A values and intercepts and things like that, how those are calculated, the book supplement does a really good job of explaining it in very simple words. I just didn't want to bog you down with that. If you have any questions, please feel free to reach out to me. And that goes for with this class, but also long after this class. As kind of one of the stats professors, you are more than welcome to reach out to me if you are working on, say, a senior thesis and you're not sure which analysis you should use, or how you need to do a certain analysis, you've forgotten the steps of it or something like that. You're also welcome to save any of the videos that I have posted, anything like that. You are welcome to keep those materials and use them down the road. I still have some of my stats materials from when I was an undergrad. I have all of my stats materials from when I was in grad school. And I go back to them pretty regularly because, frankly, if you don't do statistics on a regular basis, you will forget it. That is normal. And so you'll probably have to relearn it at some point. So I do encourage you to hold on to some of those materials.